Hey, welcome to Introducing Statistics in this course. I hope you know a little bit about it because we're going to start a little bit down the track with statistics. Have a look at some of these diagrams here. You might have seen some of this before. A histogram. What about this continuous curve here? I don't know about that one. Down here, a definition of a mean. Have you seen any of this before? And up here, I've taken some screen clippings here from Hayes and Harris. And here's a dude, here's John Sinclair, back in the 19th century, who coined the word statistics. And statistics means a few different things, but let's go back to its origin. It's an inquiry into the state, there it is, statistics, something to do with the state statistics for the purpose of ascertaining the quantum of happiness enjoyed by its inhabitants and the means of future improvement. Oh, well, that's interesting. State statistics, that's still part of the word, and we're trying to ascertain something, we're trying to measure something, a quantum of happiness enjoyed by its inhabitants. Well, I guess you know the statistics is about doing measurements and making some inferences and some conclusions from that sometimes as well. So there's the origin of the word. Interesting enough, I don't know that he was very mathematical as such, but we've gone on and developed a lot of mathematical theory around that word statistics. Let's see if I can introduce you to it in a basic way in this presentation. So come on down and let's have a look at the two types of statistics that we might consider. And in your mathematics career already, I guess you have had a look at this descriptive statistics. What you're trying to do is to collect data, collect information, make measurements and describe what's going on. And that's drawing histograms and saying, how tall are the people in your class or what were their marks, and have a look at that. And generally, in that area of statistics, we're interested only in describing what data is being collected. We actually don't make any effort here to generalise it, to say what else could be happening for a bigger group or for a whole population. Okay. And population, just mentioning that word now, does not necessarily mean people. It means a population of individuals or items that are being measured. It could be all the brake pads that are made by a certain manufacturer, and we're interested in the lifetime of those brake pads. And the population would be all the brake pads that are ever made by that manufacturer. So that's an interesting word, population we'll see later on. Here's what we're going to be doing down here. Inferential statistics. Inference means making some suggestion or inference, to infer, to suggest something about a whole population from a random sample. Okay, so we need to unpack that word in a minute. We select a random sample. We use the information from it to make generalisations about what would happen if we measured everybody, the whole population, or all the items of interest. Okay, so this is what we're mainly concerned with in this particular course, inferential statistics. And there's an interesting amount of calculation and probability around our inferences that we're going to make. So come on down, let's develop it a little bit further. Here's Huddy's favourite diagram here regarding inferential statistics. So you've got a population up here, and it may not be people, it could be things, as I said, car parts or something like that. You could be actually asking people who they're going to vote for in an election, and you can't ask all of them, so you're going to take, look at this, what does this mean? All these lines here, where this is going to be the number of people or measurements you take, this is going to be your sample. So this would be of size n maybe. I think you'd want a bigger sample than what I've got here. You want n to be fairly large. And how large is fairly large? We're going to talk a little bit about that later on. Want a fairly large sample size n to look at because this is the group that's going to represent the population, and we're going to say things about this group that we measure and make an inference back from this sample. We're going to say, hey, we infer or make an inference about the whole population. So this process is prone to error. Can you see that? To start with here, this sample is going to have to be carefully chosen, and even then it's relatively small. See this rather small size I put relative to the population, trying to show you we've got some errors going to come in here as we try to use sampling to make inferences about a population. All right, so here's something from Hayes and Harris. P meaning parameter and population. So the quantities we're trying to measure in the population are called parameters. Saying things like, what's the mean? We use a Greek letter for the mean. That is the actual mean of the population if we measured them all. And of course, physically, financially, that's usually not able to be done. You can't measure all the individuals in the population. And maybe another parameter, property of the population, the absolute value of that particular property would be maybe the standard deviation, measuring the spread, if you like, of the values around the mean. We'll come and look at the old definition of the standard deviation later on there. So we use Greek letters for the actual values of that population parameter. Okay, the actual value. So the parameter means the real values of the population we're trying to work out, and we can't actually get them directly. It may be too time consuming, may be impossible to actually do that. For example, with the brake pads, you would have to get all that were ever made and test them and burn them all out to wear them all out, and then you have nothing to sell. So you can't do that. You have to sample them as they wear out, have a look and see what inference you can make about the average life or whatever. Down here, again from Hayes and Harris, S for sample and S for statistics. In other words, when we get a small bundle and calculate a mean, we use this symbol, X bar for the mean, and that's called a sample statistic. It's a statistic because it's an S that's taken from a sample to estimate the true value, which would be called the population parameter. So we might say here, X bar approximates mu in the actual population. We're going to find an X bar from a sample, the mean, add them all up, divide by how many there are, remember that, have a look at that again later, and we're going to say that's going to be an estimate of our mean. And what else? Well, we usually use S in our sample if we're trying to represent the standard deviation, a measure of spread. So S approximates, or you could say estimates sigma in the original population. Do you get it? This is the crux of this course now. It's exciting stuff because people want to know, who's going to win the next election? How far will my tyres on my car go? How tall are people in the population overall? What's a usual average weight and things like this of everybody? And so this area of inferential statistics is the only way we can physically and financially get some idea of the population. But look out. With what degree of certainty? What's the probability that the estimates that we're making, either on the mean or the variation in scores around that mean, the standard deviation, what's the likelihood that they'll be correct? Hey, let's go and have a look. Okay, so here we have a few definitions here that I'd like you to already know. A population, a collection of individuals, not necessarily people, about which we want to draw conclusions. Census, that's when you don't need inferential statistics, right? Because you're going to go out and measure the whole population. So a census is done in Australia, I think every 4 years, and there's an attempt to measure everybody. Okay. A sample is when you can't do a census. and you've got to select a subset or a group from the population to represent that population and make some inferences about the whole population. Data, or data, whatever, comes from the Latin singular measurement, datum, information about individuals in a population. Okay, so that's usually the sample measurements, isn't it? The data that we've measured is from our sample. All right. Parameter is the actual value, a numerical quantity in this context, measuring some aspect of a population, as we're going to be doing continuous variables here, not discrete ones in this particular section. And so it's usually a continuous numerical variable, measuring some aspect of a population. Okay, so the parameter is the actual value that we would like to know about but can't get directly unless we do a census, which is going to be very expensive. A statistic is a quantity calculated from the data gathered from a sample. It's going to estimate or approximate the real value. Okay. And then the distribution is a pattern of the variation of the data, and it's also a probability distributions. We'll be talking about those as well. So distribution is trying to see how the data is distributed. Okay, I hope you've seen some of those at least before, but catch on now. Can you see what we're trying to do yet? All right, come down and have a look at this statement here about how to do some sampling. In this work, we're only going to talk about a random sample, a simple random sample, where it gives every individual an equal opportunity of being involved or being measured. And we try to use a random sample because if a sampling technique is biased, it means you've systematically selected members with certain qualities or properties and haven't chosen to make sure others who don't have those properties are also included. In other words, it favours some individuals above others. You may not have done that deliberately, but your sampling could be biased because you didn't think hard enough about giving everybody an equal opportunity of being included. And then, of course, that's all we're going to be doing in this course, but, of course, maybe you might want to structure your sample a bit better than just taking a chance. They've got the same chance of being included, but did you have the same sort of proportion of each group in the end as what was in the population you're trying to estimate? That's an interesting one. That's, of course, for further statistical study. We're not going to be doing that in this particular course, but just starting to get our heads around some of the things that are going to be operating in this area of inferential statistics. Come on down. Here we are. What do we do with an inferential statistical problem? Somewhere where somebody says, well, what do you expect to get out of this set of batteries in my torch or in an MP3 player or something? How long can I expect them to last on the average? All this sort of stuff. So we would like to know how long the population of those batteries does last. What is the mean? Well, we can't do that. But we can state, number one, the population is a set of those AAA batteries that are driving this thing. And then we will take some measurements by collecting data from a random sample of sufficient size. Sufficient size is a very, very interesting statement in statistics, because can you see that it will depend on the nature of the population? You know, how skewed the numbers are, perhaps. Are they all fairly evenly distributed, or are they really dispersed and far-ranging? How many are in the population? This is problematical in statistics. There are many theories for different sorts of problems as to what a sufficient size sample is. We won't be doing that in much detail, but we will be mentioning it later on. Okay. You want to get the relevant information from the sample measurements, usually in what we're going to be doing here, because we're going to be looking at the distribution of continuous variables here. Okay. Use the results of the sample analysis to make an inference. Okay. So what are we going to do? Maybe calculate an X-bar for the average battery life in our sample. How many would we take? I don't know, 50, 100? okay, and see how many hours we get, and make some, therefore, inference about what does that mean for all the batteries? What would that mean for mu? Could we tell people you can expect a battery life of 120 hours or something like that? Would that be a reasonable estimate of what the population of such batteries usually produces? And then, this is the interesting thing, which really does make some mathematics students particularly, a bit frustrated, because we've got to give a measure of the reliability. There won't be an exact answer, will there? Inference, we're going to make some suggestions about what we've found, but we haven't measured mu. Oh no, we haven't measured them all, because we'd wear them all out and then there'd be nothing to sell, mate. Okay, so this frustrates people, that you can't say absolutely what the answer is in inferential statistics. And it's an interesting area where you can see how statistics melds into or gives rise to the probabilities and so on. And so we will be looking at that connection. Okay, come down now and get, this is a Huddy statement, a very, very important statement here. The sample needs to be a good representation of the population if our inferences are to be reliable. Did you get it? I think we've been raving on enough about that. The sample needs to be a good representation of the population. We're not going to go into sampling techniques here. We're only going to make sure that we have a good random sample, that every member of the population has equal opportunity of being included. That won't guarantee that we do get a good representation, however. There are other factors going to come into play there. Anyway, we're going to assume here that we're going to do random sampling, and that will be a good representation of our particular population, and we want what we say about the sample to be a reliable estimate of what's going on in the population at large. Okay, come on down, and I want you to practice on some little problems here. These are from Hayes and Harris, and then we'll finish this short presentation. I want you to start thinking about the direction of this course here in inferential statistics. Okay, so it's just asking to go through the process in your mind about what we're going to be doing here, talking about a problem, what's the population, how are you going to sample it, and so on. Okay, so question 1 and 2, you can pause the presentation. Down below these questions I've got the fully worked answers from Hayes and Harris. Okay, so I'll show you the next couple then. 3 and 4, we get maybe all of 4 in, I think, mostly. Okay. Pause the presentation, just check out your thinking there. Okay. And then we have some answers. All right. Okay, so read through, start to catch the feeling of what we're doing and the language. That's very, very important in statistics, the idea of a parameter being the absolute property that we're trying to measure in the population, and we're going to use a Greek letter for that, and then our sample values calculated to estimate those. All right. Are you underway? This is going to build up fairly quickly now, so check out your definitions and terminology there, and I'll catch you in the next presentation. Cheers for now.